Welcome to the new era of video creation with BeoZ8. We will discuss, explain the concept of generative models in AI. How do they differ from discriminative models, and what are some real-world applications of generative models? Here is the content. Generative models are a type of AI model that generate new data samples rather than simply classifying or predicting based on input data. These models try to learn the underlying distribution of data, enabling them to generate realistic data that matches the characteristics of the training set. Two widely known types of generative models are GANs, generative adversarial networks, and VAEs, variational autoencoders. The primary goal of generative models is to create new data that can resemble or mimic the original dataset, such as generating realistic images, music, or text. These models are particularly useful in areas like image generation, data augmentation, and text synthesis, where new data is needed for training or creative purposes. Generative and discriminative models serve different purposes in AI. Generative models aim to learn the underlying data distribution, meaning they learn how the data is generated. They model the joint probability distribution of the data, both inputs and outputs, which allows them to generate new instances. Discriminative models, on the other hand, focus on classifying data into predefined categories. They model the conditional probability distribution PYX, which is the probability of a label given a feature, making them suitable for tasks like classification or regression. For instance, GANs and VAEs fall under generative models, while SVM and logistic regression are examples of discriminative models. The key difference is that generative models try to recreate the data, whereas discriminative models only try to distinguish between classes. One of the most popular generative models is the Generative Adversarial Network, GAN, which consists of two neural networks, the generator and the discriminator. The generator creates fake data that is intended to resemble real data, such as images or text. The discriminator evaluates the data, distinguishing between real and generated fake samples. During training, the generator tries to improve its fake data generation, while the discriminator works to become better at detecting fakes. This adversarial process continues until the generator creates highly realistic data that is indistinguishable from the real samples. GANs have shown impressive results in generating high-quality images, deepfake videos, and even generating artwork. Another important generative model is the variational autoencoder, VAE. A VAE works by compressing data into a latent space where the model can manipulate and reconstruct it. Encoder. The encoder maps input data to a latent representation or a compressed vector in a lower dimensional space. Latent space. This compressed space represents the essential characteristics of the data in a more compact form. Decoder. The decoder reconstructs the data from the latent space representation. VAEs are commonly used in applications where data needs to be reconstructed or modified. They are often used in generating images and can be used for anomaly detection or data interpolation. VAEs tend to offer smoother outputs than GANs because they rely on probabilistic methods. Generative models have been successfully applied to various real-world scenarios. Image generation, GANs, and VAEs are commonly used to create realistic images of objects, people, or environments. For instance, GANs can generate realistic human faces or artificial landscapes. Data augmentation. In machine learning, especially for tasks with limited labeled data, generative models can generate synthetic data to expand the training set, improving model performance. Text generation. Generative models are also heavily used in NLP for text generation, such as producing paragraphs of text or completing sentences. This is used in applications like chatbots, content generation, and language translation. Art and music creation. Generative models like GANs can be used to create artwork or compose music, enabling AI systems to generate creative works that mimic human artists. These applications showcase how generative models are not only useful for standard data tasks, but also have a significant impact in creative industries. Generative models offer several key advantages. Data generation. These models can create new synthetic data that closely mimics real data. This is beneficial for generating large data sets when acquiring real data is difficult or costly. Creative applications. They are revolutionizing creative industries, allowing for AI-generated artwork, music, and even novel content. Data imputation. In cases where data is missing or incomplete, generative models can help fill in gaps by generating plausible data to replace missing values. Compression. By learning to map high-dimensional data into a latent space, generative models help compress data, which can be useful for tasks such as image or video compression. These advantages make generative models valuable for both traditional machine learning tasks and cutting-edge applications in art and design. Despite their many advantages, generative models come with several challenges. Mode collapse. In GANs, the generator might produce a limited variety of outputs, failing to cover the full diversity of the data distribution. This is called mode collapse. Training instability. GANs, in particular, suffer from unstable training. Both the generator and discriminator need to balance their learning, and if one becomes too powerful, the training process can fail. Evaluation metrics. It's difficult to directly measure the quality of generated samples, and there is no one-size-fits-all evaluation metric for generative models. Common metrics like inception score or Fréchet inception distance (FID) are used, but they are not perfect. Overfitting. Just like discriminative models, generative models can overfit to the training data, especially if the dataset is small or not representative of the real-world distribution. Addressing these challenges requires careful model tuning and more advanced training techniques. There are several different architectures used in generative models, each with its own advantages. GANs consist of two networks, generator and discriminator, competing against each other. GANs are commonly used for image and video generation. VAEs use an encoder-decoder architecture with probabilistic inference. VAEs are great for tasks that require smooth interpolation and reconstruction. Autoregressive models like PixelCNN and WaveNet predict the next pixel or waveform sample given previous ones, allowing for generation of high-quality images and audio. Flow-based models, such as Real NVP and GLOW, are based on invertible transformations, enabling both efficient training and generation. These architectures provide a wide range of tools to generate diverse types of data. In conclusion, generative models have revolutionized AI by enabling the creation of new data, driving applications in various fields such as healthcare, entertainment, and design. To get the best results from generative models, choose the right model. Select the model that fits your specific task. For example, use GANs for high-quality image generation or VAEs for data reconstruction tasks. Balance model complexity. Avoid overfitting by using models with appropriate complexity and data augmentation techniques. Regularization. Implement regularization methods like dropout or weight decay to prevent overfitting. 4. Continuous evaluation. Regularly evaluate the performance using appropriate metrics, such as FID or inception score, to track how well the model is performing. By following these best practices, you can harness the full potential of generative models in your applications.